Now, the next part in our ongoing topic of normal mode analysis and thermal correction. Before we start thermal correction, there's one point which I want to discuss is zero-point vibrational energies. We know that if we talk about harmonic potential energy surface, there are many different vibrational levels available, where n is equal to 0, 1, 2, 3, 4, and so on. In quantum mechanics, it says that molecules vibrate even at 0 Kelvin. At 0 Kelvin, there is no kinetic energy, but molecules still have some vibrational component. Heisenberg uncertainty principle says we cannot know simultaneously the position and velocity of a particle. But if atoms stop vibrating, they would have no velocity and well-defined positions. So it means it's going to violate that principle. So in fact, molecules have vibration even at 0 Kelvin, and that energy is called zero-point vibrational energy. So vibration energy with n is equal to 0 is known as zero-point vibrational energy. So it means if this is n equal to 0, the energy it possesses on this axis is actually equal to 0.5 h mu. Now this energy is added to potential energy of the molecule. So it means if you talk about the total energy, which is the function of coordinates of nuclei, that is equal to the energy, electronic energy, which is a function of nuclei coordinates plus the zero-point vibrational energy. Now, in the case of zero-point vibrational energy, you can see here the summation sign. So this zero-point vibrational energy from normal mode calculation. So that is the potential energy from an energy calculation. So in this case, n is equal to vibrational state. As you can see here, 0, 1, 2, 3, 4. H is the Planck's constant, which is 6.626 into 10 to the power minus 34 joules per second. Vi is the frequency from normal mode calculation. So the zero-point energy here is 0.5 h mu, but in this case, it is 0.5 n plus 1 h mu, and so on. Now, the zero-point vibration energy has a lot of things to do with the reaction profile. It has less effect on the energy of reactants and products, or in other words, on the energy of minima, but it has an impact on the activation energies. So for example, if you compare the keto-enol tautomerization, you're starting from the keto form here, going through a transition state where a hydrogen from this CH3 is moving to this oxygen through this type of a transition state for membrane and converting into enolic form. You can see here the energy of reaction without zero-point vibrational correction is 14.6 kilocalories per mole. Now, with the inclusion of zero-point vibration energy shown by the dotted line here, the energy of reaction is 14.5 kilocalories per mole. Not a big difference, merely 0.1 kilocalories per mole. Now, on the other hand, if you look at the activation barrier is 88.0 kilocalories per mole without zero-point vibration energy correction. But with ZPVE or zero-point vibration energy, it is 84.3. So now you can see here, the energy of reaction is not much affected by the vibrational correction, but the activation barrier is significantly changed with the inclusion of zero-point vibrational energies. So the take-home message is that for reaction analysis, if you're trying to study the reaction profile, it is better to include zero-point vibrational energy for better estimation of the activation barrier. Now, These effects are nearly cancelled out for reaction energies because the effect on this minima for 0-point vibrational correction is the same as the effect on this minimum. So at the end, there is no effect on the energy of reaction, but effect is more pronounced for barriers because transition state often have weak vibrations with low frequencies, and in those cases, like these bonds here, the bond being formed here and the bond being broken here, they are weak bond and they have low vibrational frequencies, and therefore vibrational correction has more impact on this structure as compared to these two. ZPVE correction is smaller than for reactants and products and often included in reaction energies and barriers if frequencies are available. Okay, now moving to the thermal correction. All calculations by default, they are carried out in gas phase and at 0 Kelvin. For example, if you talk about calculation in Gaussian software, energy calculation methods provide the potential energy of the system at 0 K. Meanwhile, experiments are done at finite temperature and pressure. If you talk about the room temperature, which is generally considered as 25 degrees Celsius or 298 Kelvin, and the pressure is 1 atmosphere. So these experiments are governed by enthalpies and free energies. The question arises, how do we incorporate thermal and pressure effects into our calculated energies? These corrections are generally implemented through statistical mechanics to explore the properties of system in a macroscopic ensemble. So statistical mechanics will let us determine how thermal energy is distributed in the molecule, and it provides access to enthalpies, entropies, and free energies. Now, in this part of the course, I'm not going to go through the entire statistical thermodynamics here because that is beyond the scope of this course here. I will just focus on simplified equations. For example, properties are given by partition function. So what is partition function? It describes distribution of energy in an ensemble of molecules. So in the canonical ensemble, the constant NVT, where N is the number of moles, V is volume, T is temperature. So the partition function is equal to summation E power minus EI NV over KBT, where EI is energy of state I and KB is Boltzmann constant, which is 1.38 into 10 to the power minus 23 joules per Kelvin. So partition function in statistical thermodynamics is very much similar to wave function in quantum mechanics because it contains all the information in statistical thermodynamics. So with this partition function, if you ultimately calculate internal energy, it will be given by this equation. Enthalpy is given by internal energy plus PV. Entropy is equal to KB natural log of Q, which is partition function, plus KB Boltz's constant, temperature, into derivative of log of Q, natural log of Q over this temperature here under constant number of moles and volume. Similarly, free energy can be given as G, which is equal to H minus Ts. All these equations I'm not going to drive here. They are just coming from the statistical thermodynamics. Now, before going on further discussion here, the question arises, how does an electronic energy relate to a thermodynamic quantity? Electronic energies are unspeakably tiny energies referring to the potential energy of a single molecule at 0 K, which is characterized by nuclei. Electrons are treated quantum mechanically. Now, your bulk sample contains large number of molecules whose distribution is governed by Boltzmann statistics at equilibrium. Now, thermodynamic quantities describe the ensemble properties of large number of molecules. Now, the difference here is when you talk about a single molecule at 0 Kelvin is like a ball on potential energy surface, whereas 1 mole of molecule at non-zero temperature is like a dense flock of birds, which can be colliding with one another, some going up, down, right, left. So the properties of the bulk are determined by their interaction with one another, whereas an isolated molecule at 0 Kelvin is just like a ball on potential energy surface, which is isolated from everything else. So as I mentioned here, electronic energies are very small. Once we will have some calculation, I will show you that even for a small molecule like a noble gas, like if you talk about helium, and if you calculate its electronic energy, it turns around somewhere 2 atomic unit, and 1 atomic unit is about 627 kilocalories per mole. So if you talk about 2 atomic units, it's around 1254 kilocalories per mole. You might be thinking that it's a huge number, but that's not, because this energy is for 1 mole of helium atoms. And if you talk about energy per single molecule, then it will turn out that it will be a really small number. Now, the electronic energy is in fact the energy of a system where this energy is coming from interaction of electrons with nuclei, nuclear interaction, electron interaction. So it means if I say that helium has the energy of 2 atomic units, or maybe 1254 kilocalories per mole, this energy is the energy which is required to break apart helium atom into its electron and nuclei separated far away from each other, almost like at the end of the universe. Now, we know that partition function on the previous slide is a function of number of moles with constant number of moles, volume, and temperature, and that is given by e power minus ei nv over kBt. Now, if you divide or if you split this energy into individual molecules, you can write like this. For molecule 1, E1, for molecule 2, E2, and so on, where Ei is the energy of molecule 1 in state I. Now, in this case, n factorial is taken because all possible combinations that molecule can adopt will be taken since energies are written for individual molecules. So Q can be broken down into a product of partition function for each molecule, and if we apply ideal gas behavior, in ideal gas behavior, two molecules, gas molecules, they are not interacting with one another, they are behaving independently. So it means molecule 1, molecule 2, molecule 3 will have same energy. So we can write degeneracy here with GK. So GK is actually describing the degeneracy of state K, and it can be summarized as small q for individual molecule as a function of Vt power n divided by n factorial. This power n is coming because we have n number of molecules, and that is coming as power n here. And now your partition function for the bulk can be written as partition function for individual molecules as a function of volume and temperature power n over n factorial. So question arises, what contributes to the total energy of a molecule? The total energy of the molecule is coming from sum of electronic energy, translational kinetic energy, rotational kinetic energy, vibrational kinetic energy. So electronic energy is something found inside a system, and it can be calculated from Schrödinger equation or from Chem equation in density functional theory. Whereas the translational kinetic energy is coming from the movement of the molecule. It depends only on molecular weight and choice of standard state, volume, and temperature, and it will be a 0 at 0 Kelvin. So it means at 0 Kelvin, you don't need to worry about the translational kinetic energy. It will be 0. But if you are talking about a system at room temperature or temperature other than 0 Kelvin, you have some contribution from translational kinetic energy. These are dense level, just like classical system. Now, the second part, beside electronic energy, is rotational kinetic energy. I'm segregating electronic energy because electronic energy is inherently present no matter whatever the temperature is, whatever the outside environment is. So even if you have 0 temperature, 0 Kelvin, in gas phase, no pressure, you still have electronic energy. These energies are not present at 0 Kelvin. So if you talk about rotational kinetic energy, you can think about a rigid rotator. Again, it contains dense level, just like classical system. Now it depends only on principal momenta of inertia, where it depends the masses and separation between them, and also on the temperature, and again it is 0 at 0 Kelvin. Now one thing common between translational kinetic energy and rotational kinetic energy, that you don't need to do any quantum mechanical calculation. They can simply be calculated from classical system based on molecular weight here and based on moments of inertia. Now, if you talk about vibrational kinetic energy, it can be simply calculated. If you talk about harmonic oscillator, you don't have dense level. It depends on molecular vibrational frequencies. Or in other words, it depends on normal modes and temperature. And we'll see sooner that it requires quantum mechanical calculation to calculate vibrational kinetic energy. So it is not 0 at 0 Kelvin because of quantum mechanical harmonic oscillation. So you have 0 point vibrational energy present even at 0 Kelvin. So with these facts, for one molecule, the partition function shown by small q can be written like this here. You can decompose it into 4 components: electronic, translational, rotational, and vibrational components. So this EK is broken down into 4 parts. The first one is electronic, the second one is translational, the third one is rotational, and the fourth one is vibrational. And you will see here only the translational part depends on the volume. It's a function of volume. So QVT can be written as Q electronic, which is for constant temperature. Q translational is for V and T. Q rotational is for T. And Q vibrational is again for T. So we substitute QVT into expression for capital Q and then calculate internal energy and entropy. I'm not doing any complex mathematics here, just simply showing the equation. So if you talk about closed shell molecule, GI is equal to 1. When you talk about electronic kinetic energy, we are talking about ground state system because we assume that all molecules are present in the ground state. So excited states are inaccessible at normal temperature, so we only consider those ground state. And if we consider ground state, then the energy at the ground state is equal to 0. So it means we can simplify that Q electronic is equal to 1. I repeat here, Q electronic is given by this equation, and EI is the energy. And we know that under normal condition, normal temperatures, the excited states are inaccessible. So we only consider ground state, And with the ground state energy as 0, the Q electronic becomes equal to 1, and natural log of Q electronic becomes equal to 0, and U electronic is 0. So anyways, now in the case of entropic contribution, it is equal to N KB natural log of 2s plus 1, where 2s is the multiplicity, which is equal to R natural log of 2s plus 1. And this R is ideal gas constant, and we assume that N is equal to NA.